you'd have a sort of continuity. So what you would get is that d by dz, f hat z of 0 would be equal to minus, I'd have my absolute omega, I'd have my derivative, oops, at zc, and then all that would change would be that I'd have a 1 plus little o of 1. Okay. All right, so if I did that, then I could recover, I've got a sort of differential equation for, oh, sorry, yes, as z increases to zc. Okay, and actually just to save writing out this sort of hard to write term, I would actually just note that this is, let's see, it's a, this is actually a zc to the minus 1, and then plus 1 plus little o of 1. Okay, so I've got a sort of, this is almost like a differential equation apart from this little o of 1. So I need an initial condition. And the initial condition is that the susceptibility at the critical point is infinite, which means that f has the value 0 at zc. So with that, what you conclude from there is that f z of 0 hat is a zc to the minus 1. I'd get a zc minus z. And so, okay, now you have to be a tiny bit careful, but when you do the integration, you still get a 1 plus little o of 1. And, well, that's it, actually. If you unravel the statement and solve for chi and move this z inside, you get the statement that was claimed. Okay, so I just need to show that this is finite at the critical point. Okay, so what does this correspond to? So I'm going to recall that pi z hat of 0, so that's the sum over the type of configuration and this in turn I can think of it as a sum over all possible lengths with a z to the m. Got that right? Yes. Okay. So if I want to take the derivative now, I'm going to. Yes. Thank you. Okay. So when I go to take the derivative, I'm going to, well, let me edit my previously written equations. I'm going to take the derivative in the power series sort of way. So I'm going to get a z minus 1, and I'm going to get an m. Okay, so I want to check that this is going to converge. And actually, let me just isolate the term here corresponding to n. Okay, so this is a diagram with n branches, one of the diagrams that was originally on the board over there. And then what's the effect of this capital M? Well, what that means is that I've taken my diagram, and let me show you, say n equals 3. I've taken my diagram, which normally looked like this, and I've marked a point somewhere on it. So this corresponds to summing over the sum over m. And the z to the m minus 1, that's not really relevant one way or the other. Okay, so I've marked a point somewhere on it. So it could be here, for example. This is if I label my branches, it could be on the second branch. It could be on the fourth branch, say. I won't write out all 5, but it could also be on the third branch, in which case this third branch had better not be 0. Remember that it could sometimes be 0 normally. Okay, and I'm just going to bound each one of these individually. So this is actually very similar to things we've done before. So let me take this one, for example. The way you bound this, well, I'm going to, again, bound it by a picture. I'm going to say pair up the 1 and the 3. I'm going to leave the 2 with a dot, and the 4 and the 5. Okay, so this is very much similar to how some of the other bounds were proved when you did not have this marked dot. Okay, so let me just summarize by saying that the 1 and the 3 and the 4 and the 5 work out fine. And then we just have to think about what to do for the 2. Okay, so let me tell you how that goes. So what's this? So now we've got a single self-avoiding path, and then there's this 2 in the middle. But this is actually a calculation we've done before. This is the calculation that led us to the bubble condition. So I'm going to bound that by saying that, sorry, how we go? I'm going to say that we've got a, sorry, which is the picture here? Either we've got 2 let's see. Okay, sorry. I should actually not take you through this computation all the way again, because it's actually the same computation we had before. What the upshot was is that this 2.1 could be bounded by, this was, if you remember, this was Q, was bounded by chi squared times b of z minus 1. Okay, so this bound follows in essentially the same way as things we've done before, and it means that we can show that all of these are finite, essentially under this, with sort of earlier work that we've already done in looking at the bubble condition. Okay, so this is finite, and now we can run through this argument and get our asymptotic formula. Just one very quick remark about why this is so useful. Why did we really need to know A? Well, suppose you wanted to do something more fancy, like doing some sort of conditioning. So then you might have a bunch of events that you'd want to know the sizes of, or count the number of things in various ways. And you'd want to know that if you took ratios of 2 of them, for example, that you got what you expected. So if you just knew that you had some constant over 1 minus z over zc, and you took a ratio with another one that was some constant over 1 minus z over zc, you wouldn't know about the constants. But the point is that because we have this exact formula for the constant, we can get we know that they cancel, even if we don't know precisely what this value is. So Roland, I'll hand it back over to you for the problem 1. Yeah. Which one?
So if you want the solution of f is equal to a in c minus 1.
This one, yes.
Just linear series around the c, right?
Yeah, essentially. Why, pardon me?
So why zc is 1?
Sorry, what at zc is 1?
So my question is pi hat at zc is 1.
Pi hat at zc is 1. This one. You're looking at this one? Yeah, so we don't exactly know what this one is because we don't know what this one is. All that we know is that the sole sum of them works out to 0. Essentially, except that we can't do this too many times. So if you tried to do this again and differentiate twice, well, sooner or later you'd get down to a picture with 2 marked points. And then if you had 2 marked points in this branch, you would not get a bubble but a triangle, and this would not necessarily work. At least the dimensions where it would work would be different.
Okay, maybe let me continue where I stopped before. So we obtained these bounds on H, and we also have a bound on H convoluted with G. Recall that G is just H plus delta 0x. So by applying, this is basically a triangle inequality followed by Cauchy-Schwarz, we obtain a bound on H convoluted with G in terms of H, and H is small. So this series, if we sum over n, is geometrically convergent. And the consequence of this is that if you truncate a geometrically convergent series, the tail will be dominated basically by constant times the first term when you truncate. So we obtain the bound that's a sum over n greater than m, summed over x and zd pi z n of x is less than a constant times So instead of writing beta, I will usually write O of 2d to the minus 1, because the next problem is concerned with, we're interested in taking d very large. So this is in the limit as d goes to infinity. Need some more space. Yes, I can do the first part here. So problem one, in problem one, we'd like to show that mu is 2d minus 1 minus 2d inverse plus O of 2d to the minus 2 as d goes to infinity. So and this is a special result of a more general asymptotic formula for, or an asymptotic expansion for mu. Yes?
Is there a short heuristic explanation of this?
I don't know any.
Well, you've got this equation, it's gone now, but there's an equation that's obeyed by ZC that I think you're...
Oh yeah, yes, I'm about to explain that, but it's not like a hand-waving argument. So yes, this is the equation for 1 over mu, which is ZC.
Yeah, so the 2d minus 1 is saying that's what you're going to get by
Yeah.
stepping that. And then, well, the other terms are going to be what you get by not taking squares and not taking hexagons and not taking octagons and so on. So think of it that way. It doesn't tell you why the coefficients are all there.
Yeah. So looking at this formula, we need to understand what pi hat of 0 is. And recall, this is the same as, so this is a Fourier transform evaluated at 0. And this will be, okay, let's.
That subscript is ZC too, right?
Yes, sorry, this is ZC, of course. So looking at this formula, we can see that if we are interested in knowing pi hat to order 2d to the minus m, we only need to compute the first m terms explicitly, since all of the tail of the series will be estimated to this order by this formula. So we are interested in knowing pi hat to order 2d to the minus 3. So we'll need to evaluate pi hat of 1 and pi hat of 2 with 1 or 2 laces. And this is what this problem is going to be about. And before going into that, let me start with kind of a lemma that we're going to need in doing that, which is that the one norm of 1 minus d hat, all of this to the power minus m, is decreasing in d greater than 2m. So let's pause a second and see why this makes sense. If we take m equal to 1, this is just the integral. Since this term is positive, this is just the integral over 1 over 1 minus d hat, which is the expected number of visits to the origin of a simple random walk takes. So, so this statement for m equals 1, it means that, in a sense, a simple random walk becomes more transient as the dimension increases. We take m equals 2. This is the expected number of intersections that 2 independent simple random walks make. And again, this is decreasing as the dimension increases, because the walks tend to be more self-avoiding. And so this is a computation. It's it relies on a trick, but with that trick, it's very straightforward. We use the formula for a to the minus m. And if you recall the definition of the gamma function, we can express a to the minus m in terms of this integral. And since everything is positive in these expressions, we may plug that in here and use Fubini to rewrite this integral as this is from 0 to infinity. The inner integral is just the product of one-dimensional integrals, since if you recall, d hat of k is a sum of d independent of d separate terms, that d independent terms. So this is the same as, I guess, so same as e to the minus u 1 minus cosine t. And there was a 1 over d. The formula for d hat, dt over 2 pi to take all of this to the power d. So we call d hat of k as 1 over d sum cosine ki, I equals 1 from 1 to d. So, but this is just the 1 over d norm, so of e to the minus u 1 minus cosine. Okay. I have to, because there's not much space here. Yes, I just wanted to finish this exercise on this part of the board So maybe let me say this in words. So this is the L1 over d norm of this integrand without the 1 over d. And this is so we're integrating from minus pi to pi. So this is a probability space. And the LP norm increases as we increase p, so it decreases as we decrease d. So this integral will be decreasing. And will be finite under this condition.
So anyways, the formula for e to the minus m is just changing.
This is a change of variables in the definition of the gamma function.
Well, you don't need to know anything else.
No.
Just
Yeah. So this is part A on the exercise sheet. Okay. So in part B, we're going to look at a variation of what was called H here. Recall that H is a generating function for all self-avoiding walks that take at least one step. Now we're going to look at the generating function for self-avoiding walks that take at least j steps. So this is defined as the sum from over m greater or equal than j, Cm of x, z to the power m. And the claim is that this satisfies following bound, that at the critical point, the L infinity norm is order 2d to the minus j over 2. And so we obtain this estimate basically by forgetting about the self-avoidance constraint for the first j steps. So maybe let me draw a picture. So we're looking at self-avoiding walks that take at least j steps. Say this is j 1, 2, 3, 4, 5, 6, 7. So say j is 7. And it's self-avoiding. And what we're going to do is we're going to forget about the self-avoidance constraint of this part of the walk. So the rest of the walk will still be self-avoiding, but these steps can do anything. They can intersect themselves. They can intersect this part of the walk, and so on. So by this, we obtain a bound on Cn of x, which is, let me write Cm of x, which is less than C1, which is the one step, the number of one step, well, convoluted j times with itself, and this convoluted was Cm minus j of x. This is just the bound we obtained by forgetting the self-avoidance on the first j steps. So so from this, it follows immediately that that h, dc, j, say the infinity norm, is bounded by Cj times the infinity norm of C1, J1 convoluted j times with itself. This is G critical infinity. So this is obtained by just taking the generating function of this expression and moving the sum to this term, which will produce G, and we're left with this and the factor C, Z to the power j. And so now this can be, so this is the infinity norm of a convolution. The infinity norm is estimated by the L1 norm of the Fourier transform. This is an elementary fact. So we can, and also we also know that under Fourier transform, a convolution will become a product. So use that f infinity is less than f hat 1 norm to obtain that this is less than c to the power j times and now we can apply Cauchy-Schwarz to get C1 to the power j 2 norm times GC hat 2 norm. So what are these terms? Let's look at this term first. This is the I think this is the critical bubble diagram, actually. So we've seen it's finite, actually. So maybe let me just say it's finite. So, but actually, okay, I want that it's O of 1 in D. So why is that? We have seen that, okay, I'll erase this again. We've seen in the lecture that there's a so-called infrared bound, that the Fourier transform of the 2-point function, can you see this down here? That the Fourier transform of the 2-point function is bounded uniformly in K by a factor A times the 2-point function of simple random walk. And the 2-point function of simple random walk is closely related to this expression, which we evaluated in A. In fact, it's just that with m equals 1. So if we're taking the 2 norm, we need to look at the expression with m equals 2. And we've seen that this decreases in m, and in particular, it decreases in D. And in particular, it will be uniformly bounded once it's finite. So this is O of 1 in D. So what is the other term? So if you recall the following notation from the lecture, C1 is the cardinality of the step set times the step distribution, so C1 of x. So, so we obtained the expression ZC j times omega j. We're going to say in a second that this is order 1. And then we are left with d hat to the power j, the 2 norm of that. And I'm going to argue that this is O to the 2d to the minus j over 2. So maybe let's do this first. We have this expression for ZC, which says that it's 2D inverse plus a term, which, as you can see here, is of order 2D to the minus 2, because if we start the sum at 1, we're just getting the sum over all of the laces of pi. And this will be order 2d to the minus 1. And the Fourier transform is just bounded by the L1 norm here. So this is how we get order 2d to the minus 2. So what is this? So this is the same as the 1 norm of d hat to the power 2j and the square root of that. Let me forget about the square root and add it later. And this is actually the same as d convoluted 2j times with itself evaluated at 0 by the inverse Fourier theorem. So, but this is nothing else but the probability that a simple random walk that starts at 0 ends at 0 after 2j steps. So, so we're going to get a very crude estimate for this quantity in D, which, okay, let me write down what it's going to be, and then, so we divide by the number of possible random walks with 2j steps, which is 1 over 2d to the 2j. and we have the following estimate, which at first seems very crude, which essentially what this estimate does is it kind of conditions on the dimensions that a simple random walk occupies. So we're thinking of D to be very large, possibly larger than the number of steps. So in that case, a simple random walk could occupy a certain number of dimensions, and these are just the number of ways we can choose these dimensions among all available dimensions. And then within these dimensions that we've chosen, we just allow anything. We don't really require any more that it goes back to 0. But this gives us an upper bound. It's very crude, but it's an upper bound. And from this, we see immediately that this is 2d to the 2j. This is gives a d factorial, but we can also replace it by d to the j, which is only bigger. And then there is a 1 over L factorial and a j minus d minus L factorial. We just forget about this, and we'll just make the bound bigger. And there's a 2L to the 2j. And this is a constant that only depends on j. It doesn't depend on d. As I said before, we're interested in d being large. So this is O of 1 as d goes to infinity. And this is O to the 2d, or I like to write 2d instead of d, but minus j. And if we take the square root, this is exactly what we got here. So, and this kind of calculation, in the subsequent exercises, I will not do these kind of calculations in detail. I will draw pictures and argue that it follows very, very similarly to this argument. So let's go back to what we wanted to evaluate. We wanted to evaluate what pi hat is. And we saw that it suffices to understand what pi 1 and pi 2 is, only 1 or 2 laces. We need to understand if we want to know what pi hat is to order 2d to the minus 3. So part C is pi hat Z1 at 0 is equal to C critical is equal to 2d inverse plus 3 2d minus 2 plus O 2d minus 3. So we're going to derive this. So what is pi hat 1? So pi 1 this is a generating function for all self-avoiding returns, maybe. I think the exercise sheet says it's all self-avoiding polygons, but I think to comply better with the terminology of the lecture, these are not polygons. Since we are interested in the starting point, we are also interested in the orientation. So I think maybe should correct that to self-avoiding returns instead of self-avoiding polygons. These are all walks which are self-avoiding, but return to the starting point at the end. And so how many possibilities are there to do this in 2 steps? There's only one possibility. We can step to a neighbor, and then we step back immediately. So this are all the possibilities to do a self-avoiding return in 2 steps. And there are 2D of these because there are 2D directions the walk can go into. So this is 2D times z squared. And how many possibilities are there to do this in 3 steps? There's none. Maybe I should have said there's none to do this in one step. There's also none to do it in 3 steps, but there's one, or there's several to do that in 4 steps. So what can we do? We can step to a neighbor, and so there are 2D choices to do this. So we have 2D. Then we can step to another neighbor, but we should not step back or not step forward, because then we won't be able to get back in 4 steps. So we have to step to this neighbor or to this neighbor. Let me draw this neighbor. And there are 2D minus 2 choices to do that. And then the remaining 2 steps are already determined, since we have to go here and here to go back to the starting point. So these are the number of walks with 4 steps. And then there are all walks which take at least 6 steps. Again, there are no walks with 5 steps. And so we can calculate the first 2 terms very explicitly, and we're going to argue that the remainder will be O 2D minus 3, and it just does not bother us for this result. Okay, let's. So essentially, I'm going to be. Oh, actually, could you? Well, anyways, it's okay. So I'm going to be waving my hands a little bit to estimate this remainder, because it's basically the same calculation as this one that Jesse's just erasing at the moment. These are self-avoiding returns that take at least 6 steps, so we can weaken the self-avoidance assumption on the first 6 steps. I guess these are only 5, but well, let's make it 6. So we can weaken the self-avoidance assumption on these first 6 steps. And as before, this is going to give us a factor 2d to the minus 6 over 2, which is 2d to the minus j, just as an exercise B. And what are the other 2 terms? There's one thing that seems a bit disturbing, that it depends on ZC, which is the quantity we're trying to evaluate in the first place. But we can proceed as follows. So recall that ZC is equal to 2D inverse plus, I think it's a minus, right? Is it a minus? No, it's a plus. Plus 2D inverse pi hat ZC at 0. So we know that ZC is 2D to the minus 1 plus O of 2D to the minus 2. So plugging that in here gives us an estimate for pi hat 1. So we're plugging this in here. This gives 2d to the minus 1 plus, then there's 2d to the minus 1 times this term. No, sorry. Okay, sorry. It's 2d to the yes, it's 2d to the minus 1 times so yeah, okay, so I think I actually wanted to do a different step first. Maybe let me do it the other way around. Do you have the cloth? So because what we really need here is pi and not pi 1. So let me write down what pi is. Pi is minus pi 1 VC hat plus O of 2d to the minus 2. This is the estimate we obtained from the conversions of the geometric series on the board to the left, 0 here. So now we can plug this, now I plug this into here and obtain that ZC is 2d to the minus 1 minus 2d to the minus 1 pi ZC hat 0, the 1 here now, plus O of 2d to the minus 2. Minus 3 actually, because we have a minus 2 here, and we're multiplying it by another 2d to the minus 1. So this will be 2d to the minus 3. So this is, and now we can plug in what pi 1 is using, so we have a formula. So we use this, we use the formula that ZC is 2d to the minus 1 plus O of 2d squared. Plug that into here to get a formula for pi hat 1. And then we use that formula again to plug it back into the formula for ZC to improve this formula to a higher order. And what we get is that this is 2d to the minus 1 times 2d to the minus 2 plus O of 2d to the minus 3. And again, we can use this formula to plug it back into this formula to obtain a better bound for pi hat 1. Because so far we've only obtained a bound for pi hat 1. No, we want to obtain a bound for pi hat 1 that's O to the 2d to the minus 3. And the bound we had on ZC was not good enough to obtain that, because we need to plug in ZC in here. So now we have obtained a better bound on ZC, and we can use this one to plug it in here. So, and then we get a bound for this. So there's going to be, so if we plug it in here, there's going to be this term contributing here, which gives us a 2d to the minus 1. But then the 2d to the minus 2 term well, if we square this, which is z squared, which we need to plug it in here, we obtain two terms that combine the 2d to the minus 1 and the 2d to the minus 2 term. So this gives a 2d to the minus 3, along with a 2d gives 2 times 2d to the minus 2. And then we evaluate this term. And to order 2d to the minus 3, there's only the leading term that survives, so we get another 2d to the minus 2 plus O of 2d to the minus 3. And this is just 2d inverse plus 3 2d to the minus 2 plus O of 2d to the minus 3. And I think this is the formula that's written down here. To obtain the result to this desired order, we also need to evaluate pi hat 2, 0, which is kind of similar to that calculation. We don't have a lot of time, so again, I'll be going through this. I'll try to go this kind of quickly. Let me just say what pi hat 2 is. So this is my 2's, and the z look very similar. So it's not the same. These are all diagrams, all walks which look like this. So they start at 0. They visit the walk visits its endpoint x, which will be summed over, and then returns to 0, and before going back to its endpoint. So we draw a diagram like this. And the claim is that this is 2d to the minus 2 plus O of 2d to the minus 3. Maybe let me just write down what the first terms are, not evaluate the remainder. You got the idea how it works. It's just more of the same since we don't have very much time left. So what kind of walks are there that fall under this category? So if there's none with one step, since we need to make at least one step to the endpoint, then return to 0, and then go back to the endpoint. So there's going to be at least 3 steps to do this. So the first term has z to the 3. And there's 2d of them. Why is that? We return to the endpoint, which has to be neighbor. Then we go back and go back to the endpoint. So this, and the only choice is the initial direction. So there's 2d of them. And so there's none with 4 steps, but there's some with 5 steps. And what are the possibilities? We can step to the endpoint, which has to be a neighbor. And then we return to the origin before going back to the endpoint. This is one possibility. So there's 2d choices for the first step. There's 2d minus 2 choices for the second step, and the remaining steps are determined. So this is 2d times 2d minus 2. But then there's also other possibilities. For example, we could first step to the endpoint, then step back to 0 before. Actually, this is supposed to be the endpoint. So we could first step to the endpoint in 3 steps, then return to the origin and go back to the endpoint. So there's another possibility. And there's a third one, which is first stepping to the endpoint, then going back immediately, and then going back to the endpoint. So there's 3 in front. And this will be true to order 2d to the minus 3 by evaluating like the remainder as in the spirit of what we did there. So plugging in the value for zc that we have obtained over there, we get this formula. And then we know pi 1 and pi 2. And putting everything together, we know what, get a formula for pi. So this is minus pi 1 zc hat 0 plus pi hat 2 zc 0 plus O of 2d to the minus 3. That is equal to minus 2d inverse minus 2 times 2d to the minus 2 plus O of 2d minus 3. And so this formula can be used along with this formula for zc to obtain a formula to zc that's good to order 2d to the minus 4, and inverting it gives the desired formula for mu to order 2d to the minus 2. Sorry, it was a bit technical, but I think time is up, so we should finish. Okay, thank you. Are there any questions? Yes. So the infrared spectrum is that of short wavelengths, and long wavelengths are low frequencies. and k is kind of the frequency, and where this bound is like effective is when k goes to 0.